both a bottom-up and a top-down approach. And for, I guess I should label this question, this is question 2. So for question 2, we determined the recurrence relation for this Towers of Hanoi recursive algorithm. And then we solved it yesterday using a bottom-up approach. So I'll say yesterday. And when I post the full solution, it'll have that bottom-up approach as well. But we didn't have time to do the top-down approach during lecture yesterday. So I wanted to quickly go through this top-down approach. Then we are going to move into our next unit, Unit 4, which focuses on proofs. I want to work through a few proof exercises today, just so we can get to the kind of the meat of Unit 4 for Friday's lecture. I guess depending on where we get today, that'll determine what kind of pre-lecture videos I create for Friday, and obviously the associated quizzes. So I'd like to get pretty far in so we can cover some of those the main focus of the unit for the lecture videos, and then work on those associated exercises on lecture for Friday. Yeah, I'll try and upload all of the lecture recordings as soon as I can. So I guess before we jump into this exercise, are there any questions? I guess I don't actually have the pseudocode here, but I guess, are there any questions as to how I, from this kind of recurrence relation up here, how I kind of wrote this stuff on the left? So again, what we've got is, I've said if t of n is equal to 2 of tn minus 1 plus 1, then I can, if I want to write t of n minus 1, that's going to be equal to 2 of tn minus 2 plus 1. And t of n minus 2 is going to be 2 of tn minus 3 plus 1. And I can kind of keep doing this process all the way down, and where n is decreasing by 1 each time. And eventually I'll get to t of 2, which is 2 of t of 1 plus 1. And we know from our recurrence equation up here that when n is 1, we've got that our solution is just simply 1. So our bottom up, what we did is we solved this, and then from there we worked our way back up. We said, okay, if t of 1 is 1, then t of 2 is going to be 1 plus 1. Or sorry, 2 of t1, which is 2, plus 1, which is 3. And if t of 2 is 3, then t of 3 is going to be 2 times that plus 1. And we worked our way up, and we looked for a pattern. Thanks, Finn. So now what we want to do is solve this same thing with a top-down approach. So again, we're going to start with our equation, which is t of n equals 2 times t of n minus 1 plus 1. And what we're going to do is repeated substitution here. So what we know here is that over here, I wrote down what t of n minus 1 is. So I can replace this t of n minus 1 term here with the right side of this equation here. And that's all I'm going to do. So what I can do is if I make that substitution, I've now got 2 times, making that substitution, 2 of t of n minus 2 plus 1 plus 1. So again, I've made the substitution in here for t of n minus 1. And then what we typically do after that is just collect the terms. So I've got 2 squared times t of n minus 2 plus, so I guess this is going to be plus 2 times 1 plus 1 plus 2 plus 1. So I'm actually not going to fully collect these terms. I could, but what I'm going to see, or what we're going to see is that by writing in this form is going to help us later. So again, I can now make the same substitution or a similar substitution here, I know that I can substitute t of n minus 2 because I've got that over on the left side as well. So I'm going to just replace that t of n minus 2 with 2t of n minus 3 plus 1. So when I write that out, we've got this here. Oh, yeah, I forgot the 2 here. Sorry. Yeah, I just didn't do that substitution correctly. So now, again, I'm going to see that I can rewrite this as I've now got another power of 2 here. So this is going to be 2 to the power of 3 t of n minus 3. And then again, we're multiplying 2 to the power of 2 plus 1, which is 4 times 1, which is going to be plus 4 plus 2 plus 1. And why I'm writing this is we're going to kind of see that we're going to come up with a pattern here, and we're going to use this pattern to determine the closed form expression. So what we might see here now is that this can be written as 2 to the power of 3 t n minus 3 plus 4 plus 2 plus 1, which is plus 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. So I'm just only writing this as 2 to the power as powers of 2. So what we might see here is that I can eventually write this as t of n equals 2 to the power of I, because again, these some important things to kind of see here are that we've got this number matches this number, which is also the highest, and then we've got powers of 2, one number lower than that value down to 0. So if I represent this as 2 to the power of I, what I'm going to have is that's going to be times t of n minus I plus 2 to the power of I minus 1 plus 2 to the power of I minus 2 plus all the way down to 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. Yeah, and some of you have already solved this. So what we now like to do, our next goal, which again I kind of highlighted in the videos as well, is that we now want to get rid of this this term here. We'd like to substitute that with t of 1 over here, because then we've got a known value. So we'd like to do this. So to do that, what we need is n minus I to be equal to 1. So solving for I, what that'll get us is, again, if we add I to both sides, oops. So if we let I be n minus 1, we can rewrite this as two to the n minus 1 times, times t of 1 plus 2 to the I, which is n minus 1 minus 1, plus 2 to the n minus 1 minus 2 plus all the way down to 0. So again, we know that now this is just going to be 2 to the n minus 1 times 1 here, because that's just a 1, plus 2 to the n minus 2 plus 2 to the n minus 3 plus da 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 all the way down to 2 to the 0. And so now this is very similar to something we've seen before. And I guess this is kind of something that maybe some of you have seen from working with binary numbers. Because again, if we write all the powers of 2 down, we don't even have to do this. All the way up to whatever 2 to the power of n is. When we add these numbers together, how can I do this in a clean way? Adding the numbers from here gets us 3. Adding the numbers, the first 3 values gets us 7. Adding the first 4 values gets us 15. Adding the first 5 values gets us 31. So when we add up all the powers of 2 together, that value is always the number 1 power higher minus 1. Sorry, I screwed up that last one. And we get that from binary numbers. If we think about this as just as a binary number, again, if we've got these are kind of ones in all the binary digits. So what we see is if we're adding 2 to the power of n minus 1 plus 2 to the power of n minus 2 plus 2 to the power of n minus 3, we're adding up all these powers of n. And when we add up all those terms, that's going to eventually get us to 2 to the power of n, or 1 smaller than 2 to the power of 1 power higher than our highest term. And that, and Lucas, and that's how binary numbers work. Again, if we think about binary numbers, those of you that don't know it, we've got we want to be able to count up to each number. So again, if we've got a number like when we're counting up, we've got that's 1, that's 2, that's 3, that's 4, that's 5. Where I guess these should be in this column here. Again, every binary number, when we've got all ones, it's always 2 to the power of 1 number higher minus 1. Because, again, these all being ones is 8 plus 4 plus 2 plus 1, which is 15. When we count up 1 higher, we're going to carry a digit over and get 1, 0, 0, 0, which should be 16. Again, just by the way that counting works. Yeah, it's cool. So again, what we saw, I believe, again, I don't have it in front of me, but I believe what we saw when we did our bottom up, I believe our bottom up got us T of n equals 2 to the n minus 1. Because I think what we saw is T of 1 is 1, T of 2 is 3, T of 3 was 7, then 15. So again, we're seeing these same numbers that we saw down here. So the pattern we saw, that's always powers of 2 minus 1. So the question, could we go top down or bottom up for any question? I think you technically can, but if you think about the pre-lecture video, when we had our occurrence relation was a T of n. One of our terms here was T of n over 2. So doing the bottom up with that approach is, we know our smallest term can maybe again be 1, or can be 1. And then from there, we can go up to T of 2. And then from there, we can go to T of 4. And then from there, we can go to T of 8. So it's harder to go bottom up because we don't just have terms 1, 2, 3, 4, 5, 6, 7, 8. Our bottom up is a little bit different because we don't have every single term as we go bottom up. So I think for solutions where the recursive relation, the recursive part of it is just n minus 1, it's easier to go bottom up. But when we have other things like an n over 2, it's more difficult, at least for me, to go bottom up. And I find that the top down approach works a little bit better. Because going bottom up, when we've got this, we can actually, if we try to actually do a T of 3, that's difficult because that's going to be equal to T of 3 over 2, which is T of 1.5, which we don't actually have. Yeah. Any other questions about this? So, yeah, you'll get more practice with this in upcoming labs and in the upcoming assignment. I can also dig around for some other additional exercises as well, and maybe just when I post a solution to this, I can try to post another one, just because we did only do 2 exercises, but I'll see if I can find some more practice material as well. But again, you will get more practice in the labs and the assignment. The midterm, I think, is in 3-ish weeks. What is it right now? Isn't the midterm on the 8th or so? 1, 2, 3. Let me check. The first midterm is on June 9th. So that is exactly 1 day less than 3 weeks. So just under 3 weeks. So you'll have another assignment before the midterm, and you'll have obviously another few labs before the midterm. So you'll get lots of practice with this stuff. And I'll talk about where the cutoff is as we approach the exam. It'll probably be at the end of the next unit. So the unit we're going to get started with today. Any other questions? How long has it been? I haven't even started building it yet. Again, we'll kind of see how far we progress through the next units, and then based on kind of the topics covered, I'll start thinking up the types of exercises and distribution, and I'll give a lot more details as we get closer. You shouldn't have to cancel any appointments you have that day. Okay, I'm going to stop sharing this, and I'll jump us over to the other. So I just opened up our course outline to see the midterm date. And as many of you in the chat were saying, it is on June 9th. But again, we're going to have another assignment that I'm going to give out in a few days. I think it's next Monday. And it'll be due over a week before that midterm. So I'm hoping that we can have both the first assignment and the second assignment graded and back to you, so you can have that feedback to study from that for the midterm. And then I'll provide my own solutions to each of these as well. So yeah, we've got quite a bit more material to get through, and also you'll have plenty of practice material. So generally, when I build the midterms, I will be looking at the, I guess, worksheet exercises we've done. I'll also certainly look at the assignment questions and the lab exercises as well. So if for those of you that like to kind of start thinking about this ahead of time, which is really good, I think, again, just the lecture worksheet exercises, the lab exercises, and the assignment questions are the types of exercises that I think you should practice with and kind of make sure you understand. And be sure to come to office hours if you're having trouble with anything, even if it's stuff from a while back. So what I'm going to do is, so in the schedule, what I've done is I've posted, worksheet over here. So on my screen, the chat's kind of blocking this, but I think you can all see this, hopefully. What we've got is, that should be counting operations. I posted a solution to the stuff we completed yesterday. I haven't posted a solution to the recurrent solutions, but now that we finished the last problem, I will post this after lecture. And then this proofs is what I'd like to work on today. So today we're actually going to jump straight into actually just working on some exercises for proofs. And I've got fairly brief explanations of these different proof techniques. So this is what I'm trying to do is look through previous offerings of this course and also kind of look at the associated textbook readings for each of the topics they cover. And again, just try to make sure we cover the same learning goals and meet the same learning objectives as what's been happening in previous offerings of this course, as it is my first time teaching this course. So it looks like in the last two sections or times this course was taught, again, they kind of, the slides for this unit really just has these different techniques with really this explanation I've got here. Sometimes I've added a little bit of things to that I feel like help clarify some of these definitions. But what I'll do is I will, depending on where we get to today, I'm hoping that we'll kind of get through at least this first column. What I'll probably do is add some animated slides and go through them for the lecture video for Friday, probably on something, probably by on an induction proof. But again, as I said, we'll see where we get to. So can I zoom in on this? I've got my tablet over top of my keyboard, or my laptop keyboard. Let me just take it off for a sec. Okay, I'll try and put it back on top. Okay. Yeah, so have you seen induction before? That was in Math 122? Okay. Okay, so I was going to introduce it in a video. Maybe if you've seen it before, I won't, but or maybe I can just do a video on it just to as a refresher. So have you done have you seen all these different types of proofs in Math 122 before then? Oh, okay. Okay, so then maybe we'll move through this a little bit more quickly than I previously expected, which is fine. And maybe you would have actually already seen some of these examples. Again, it seems like, especially kind of for the contradiction proof we see on the right side here, that one's kind of seems like the standard contradiction example that is typically worked through, but we'll see. Let me grab my annotation pen. Okay, so first of all, for counterexample, really all we're trying to do is find an example which proves that this doesn't work. So for us here, what we want to do, one sec. So let me try resharing this one more time. I'm gonna have to. Share screen. Okay, I'd like to get this so I can actually get the chat up as well. Proofs like that we've done before in 122 might be different if you have different proof standards. In 122, we could do written proofs instead of a purely algebraic one. Okay. Yeah, we'll see. I think it'll be probably similar. It seems like, as I said, I noticed in the previous two terms, it did seem like it was an overview of proofs as opposed to this is how we do this proof, this is how we do this proof. It was kind of like it was kind of one slide on each proof with here's an example that you should do to refresh yourself without even actually going through them. So we're actually going to do an example of each proof, which maybe wasn't done in previous slides or previous sections, because I guess they are assuming that you've already developed these skills in the prerequisite course. But we can spend some time doing them today. I think it will be a good refresher, and then in the upcoming lab and in assignment 2, you'll get to again go a little bit deeper with some of these. So for this first one, oh, I need to get my pen again. So for this first one, all we want to do is find values such that a squared plus b squared does not equal a plus b squared. And I think there's a ton of values that do this. Let's just let a equal 4 and b, oops. We let a equal 4 and b equal 5. We have 4 squared plus 5 squared. Oh, sorry. Which we'll see is not going to equal 4 plus 5 squared. So again, we've got 16 plus 25, which is 41. Oh. Does not equal 9 squared, which is 81. Yeah, we could even do 1, and yeah, we could do much simpler terms as well. So yeah, the proof by counterexample is just we're finding an example that shows that this doesn't work. Any questions about this one? Okay, I will wait one more second and I'll clear it off. Okay. So next example we'll do is a direct proof. So if n is an odd integer, then 3n plus 7 is an even integer. So again, we can assume n is an odd integer. And what this means is that we can write n as 2k plus 1, where k is an integer. Because again, 2 times, if we multiply any integer by 2, we know that that's going to be an even number. So if we multiply an integer by 2 and then add 1 to it, we know that that's going to be an odd number. So if we're assuming n is an odd number, then there exists an integer k where 2 times k plus 1 equals n. So now, if we substitute this k value for n into the expression above, so we had 3n plus 7, we can now write that as 3 times replacing n with 2k plus 1 plus 7. 3n plus 7, yeah. And if we multiply this out, we've now got 6k plus 3 plus 7, which is 6k plus 10. So now what we've done is we've rewritten we can rewrite 3n plus 7 as 6k plus 10. But what we see here is 6k plus 10 we can factor out a 2 here, which is 2 times 3k plus 5. And again, when we first assumed n was an odd, we said that we can write n as 2k plus 1 because we know that multiplying anything by 2 will produce an even number. But now, again, we know that this is an integer. So again, if k is an integer, then 3k plus 5 is going to be an integer. So since 3k plus 5 is an integer and we multiply it by 2, it follows that 3n plus 7 is going to be even. So if 3n plus 7 equals some integer multiplied by 2, we know that it's even. Any questions about this? 3. Okay. I will clear it off then. Scroll down. I can scroll down a bit further, but maybe not. Okay, so contrapositive. The contrapositive of P implies Q is the implication, not Q implies not P. So yeah, I add the Wikipedia explanation here where it says that the contrapositive of if there's A, then B, the contrapositive of that is if not A, then not, sorry, if not B, then not A. So in this case, our A here is here and our B is here. So to do this, the contrapositive proof, what we're going to say is if not B, then not A. So I guess to start with our not B in this case, our not B would be not n is odd. So in that case, what we're going to do is we're going to start by saying assume n is even. That is not B, or alternatively with the formula up there, not Q. So again, similar to what we did in the previous exercise, then n equals 2k. So n equals 2k for some integer k. So again, if n's even, then it means that 2 times some other integer is equal to n. So thus, very similar to what we did before, 5n minus 7 can be written as 5 of 2k minus 7. We can multiply out these terms. We've got 10k minus 7 And now what we've got here is 10k minus 7 can also, we can try to factor out a 2, and what we get is we see if we factor out a 2, it's going to be 2 times 5k plus 4 would be plus 8 minus 1. Or I could do 5k. Oh, sorry. 10k minus 7. Sorry. So that would be 10k minus 8 plus 1. Sorry. Yeah. So what we've got here is we can factor out a 2. We can get 2 of 5k minus 4 would be 10k minus 8 plus 1, 10k minus 7. Yeah. And again, so now what we've got here is we've got this form. We know that, again, this 5k minus 4 is going to be an integer. Um, 2 times 5k, oops. 2 times 5k plus 4 is odd, meaning that that 5n minus 7 is odd. So we now showed that when we have, we showed that if we have not B, then we also saw that not A. So again, we saw that the not of 5n minus 7 would be is odd, is also true. Any questions about this? Okay, so the next one, let A and B be sets. So have you guys worked, did you guys work with sets in 122 as well? Yeah, you did. And yeah, that was it. So we're just saying that for the contrapositive, we're showing that, again, not Q implies not P. So we said when we've got not Q, which was N is even, that implied that not P was true, which is 5n minus 7 is odd. Oh, it was set city. Okay. So when I saw this question, I wasn't really sure how to draw it out. But so again, if we've got kind of sets A and B, we know that A is kind of all of these, is all of them across both sets. And we know that, or what don't I do? So I guess what we've got here is what we want to do is for our contrapositive is we want to say if B is not a subset of A, then so we're saying if not this, then not this. So again, if we think about if B is not a subset of A, then really what that means is there exists an element X that is in set B, but not in set A. So again, we've got some X over here. So now, if we, I guess, compute this, so now if we try to do this, what we'll see is that it is actually going to be A, and it's not going to be this A, because it's going to be A and at least the element X. So therefore, we know that it's not going to be simply A, because we've shown that there is at least one. If B is not a subset of A, there exists at least one element out here. So when we try to determine this, as long as there's at least one thing in B, this is not going to be just simply A. I think I kind of screwed this up a bit. Any questions about this? We're always doing, again, this was, this is if A, then B. So we said if not B, then not A. I guess then we've also in the other notation we've kind of got if this is P and this implies the second thing Q, we've shown that not Q implies not P. Does that make sense? Any other questions about this? I'll put the chat over here now. So I guess for the contradiction proof, is this the example that you already saw in 122? Okay, so you've already seen this. Okay. Okay. Yeah, yeah, I can. Yeah, we can do a quick recap, and then that will hopefully get us right to our induction, which I can do as a lecture video. So what we're going to do is we want to show that. So if we've got this thing P implies Q, so if we're saying root 2 is irrational, we want to show that I guess the negation of this involves a contradiction. So if we're saying we want to essentially show that if root 2 is not irrational, so if root 2 is rational, that we're gonna come up we're gonna find a contradiction. So let's say, whoa. So if root 2 is rational, what a rational number just means that is that we can write it as a fraction of two integers, a over b, where a and b are integers. There's a couple other things that we're going to think about for this fraction. We want this fraction to be, again, if it's a rational number, we can write it as a fraction in lowest terms, which means that, I guess, a few things. First, b is not 0. And either a is odd, or I guess I can say at least one of a or b must be odd. I'm going to write this. At least one of a or b must be odd. Yeah. And I guess at least one of a or b must be odd. Because if they're both even, that means we could simplify it further into lower terms. So otherwise, we could just simplify the fraction further. So again, if root 2 is a rational number, we could write it as a fraction a over b in lowest terms. So again, we want b to not be 0, otherwise we've got a divide by 0. And we want at least one of a or b to have to be odd, otherwise we could kind of simplify this into lower terms. So if a over b equals root 2, then if we square both sides, we have not 2 squared. Then we know that a squared divided by b squared equals just 2. And if we multiply b to both sides, we get a squared equals 2b squared. So now, again, because b is an integer and we're squaring it and multiplying it by 2, we know that because b is an integer, we're squaring it, that's also going to be an integer. And any integer multiplied by 2 is going to be an even number. So we know now that a squared is even. So with that equation, we know that a squared is even. We also know that the square of any odd number is odd. So any odd number, 3, if we square it, it's 9, which is also odd. 5, 25, also odd. 7, 49, also odd. 9, 81, also odd. So we know that if a squared is even, that means that a itself is also going to be even. So this also means that B must be odd. As we declared earlier, to write A, B in lowest terms. So we know that, again, by these few steps here, which wasn't actually difficult, we were again just squaring both sides, multiplying by B. That told us that A was even. And before, again, to write this A divided by B in lowest terms, we knew that one of those numbers had to be odd. So now, in order for root 2 to be rational, we know that A is going to be even and B has to be odd. Yeah, that might be the way you did it before, but yeah, the contradiction is going to be that one of these values is going to be both even and odd. So a similar thing that we did in our other examples is come up with an integer k Since A is even, we know that there is an integer k such that 2 times that integer equals A. So now I'm just going to replace that here. So if we had A squared equals 2B squared, we can write this as 2K squared equals 2B squared. Sorry, let me rewrite this one. I'm going to write this a little bit smaller, else I'm going to run out of room. So we can write this as 2K squared equals 2B squared, which equals 4K squared equals 2B squared. And we can divide both sides by 2. So now this looks very similar to something we had up above, where we're now saying, okay, B squared is equal to 2 times some integer squared. So this means that B squared is even, and thus B is even by the same kind of thing we talked about earlier, because again, any odd number squared is going to be odd. So if we know that B squared is going to be even, then B is going to be even as well. So this right here is a contradiction. So that's our contradiction. We have shown that B must be both even and odd. Therefore, our initial assumption that root 2 is rational is false. So root 2 must be irrational. So I know a lot of textbooks kind of do this with a lot less writing. I kind of wrote this as a story. But I think what you kind of see is most of this kind of description in between all of the kind of algebra is skipped. They kind of just say, they kind of do the part I've underlined in purple here, and then basically just say, therefore A is even, and there exists an integer k such that 2k equals a, and then from here they just kind of finish the proof, and just right here they say, okay, now we've shown that b is even and odd. I kind of added in some filler text just to kind of fill in some of the pieces, as opposed to just doing only the math steps. Andy, they did the story or they didn't do the story? Oh, okay.